So good Monday afternoon, everyone. Welcome to, I believe, lecture 22 of Maths for Construction. What did we do last time? Last time, lecture 21, we kind of covered dimensional analysis in as much detail as I wanted to go into for what it is I wanted you to be able to do with it, right? The primary use of dimensional analysis for us is not showing an equation is dimensionally consistent, right? That's not the primary use of it. It's really deriving a formula. The question on your assignment on dimensional analysis is about deriving a formula, okay? So this example 2 that I did here, as well as example 3, should help you thoroughly with the question you have in the assignment, okay? It's not much very different from this. Today, we want to talk about the last topic, which is a statistics topic, right? So what I'll do, I'll spend a couple of minutes typing up the notes and then we will go over it, okay? So I might be silent for a while, typing this up, and then I'll start back the recording. So just hang in there as we move to this last part here. Okay, so the normal distribution. So we came up with the idea of a distribution. We saw it in lecture 20. And even before that, in lecture 19, if we go back to lecture 19, there's the idea of a probability distribution, right? A probability distribution essentially is, a function, if you want to call it, for telling you what the probability is of something happening based on a particular value for a variable, right? So we saw the probability distribution for getting a certain number of heads when you throw a coin 2 times. If you throw a coin 2 times, you could get 0 head, 1 head, or 2 heads, right? And the probability of each value, 0, 1, 2, is these here. So you get a distribution of probabilities. Naturally, for these things, what arises is a discrete variable, right? Every total probability is 1 is called random. And then a discrete variable, because variable x could only take on discrete values, 0, 1, and 2, okay? So we talk about probability distributions here, but that was a discrete distribution. And the binomial distribution is the most common discrete distribution, okay? Where you have some variable, could have discrete values. And if it's distributed binomially, it means that the function that generates the probabilities is this function down here. Where is it? See, it have n choose a, where you have all the factorials, something happening, right? So we say x is distributed in a binomial way with parameters n and p. Distributions have parameters which govern how the shape of the distribution, right? How it behaves, and it affects the probabilities assigned to x being one of these variables. So that's a binomial distribution, but we have a continuous data, right? Think, you measure the heights of everybody in a class, right? Height is not a discrete measurement. Height is a continuous measurement. We don't really have exact values for height, but we have ranges, right? Because it's a floating point number, okay? So the height could be 1.2679. That's not like discrete data like 1, 2, 3, 4. So height is because it's continuous data, we more interested in finding out what's the probability that the height of a person is less than a certain value or more than a next value or between 2 values, rather than asking what's the probability the height of a person is 5.2839 meters, you know what I mean? So with continuous data, we're not interested in finding out exact values of the variable. We're more interested in the range of values that the variable could have, what's the probability is in that range. Therefore, you end up with continuous distributions because you're modeling continuous variables. So the normal distribution is a continuous distribution. It's a probability distribution, so that it tells you what the probabilities of something happening based on what values you're interested in. But it's not discrete data you're asking, it's more continuous data, which we will see in a while. So it turns out that many quantities in nature follow the normal distribution. Okay, and we give examples here. The heights of people, masses of flour in a factory, the ages of trees in a certain part of the forest, random errors, say examination results, right? It follows a normal distribution actually. Okay, so it's one of the most important continuous distribution, and is one of the most important distribution in statistics. Now, discrete distribution has something called a probability. What we call it here? The probability distribution. Here, the discrete values. We have a probability distribution function. Okay. So say here we have. Look at it here. This is the probability distribution function. It's for a discrete variable. So because we could count it 0, 1, 2, 3, 4. But for a continuous variable, we have something called a probability density function. And a probability density function is a continuous function where the probabilities is given by the area under the curve. So you see the normal distribution has two parameters, mu and sigma squared. Sigma squared is variance, as you see up here. Recall what variance is, right? Variance is the standard deviation all squared. The symbol for standard deviation is sigma. The symbol for variance, we just say sigma squared, okay? Mu is the symbol often used with the mean or the average, right? That sum of everything divided by the number of things, right? The probability density function for a normal distribution is very complicated. This is it here, right? And it's between minus infinity and plus infinity. This is not something you want to integrate, okay? Many years ago, I tried to integrate this, and after spending like a half an hour, I could only integrate it between the ranges of minus infinity to infinity to show that the area under the curve is 1. I couldn't even integrate it between two ranges. You know, I needed to write a computer program to do that. This cannot be done analytically. It can't be done with pen and paper analytically. It could be done in pen and paper numerically, using algebra and some numerical analysis techniques to estimate what the area is. Computers are great for these things because computers are great at doing arithmetic, okay? So the parameters are mu and sigma squared, just like how, you know, the binomial distribution have n and p. N is the number of independent trials, p is the probability of success in one trial. Here, the parameters are mu and sigma squared. Mu is the mean of the distribution and sigma squared is variance, okay? We have some features here now. It's symmetrical and bell-shaped about the origin. The y-axis goes through the line mu, right? So the average is the dead center in the middle. Approximately 90% of the distribution is within 2 standard deviations of the mean, and almost 99.9% of the distribution between 3 standard deviations of the mean, right? How you find probabilities? Find probabilities by finding the area under the curve, but you don't want to integrate this function here, right? So the idea really is we use tables, tabular values. So the probability that x is between 2 values, say a and b, is given by the area under the curve between a and b, as is shown in the diagram there. And we use tables for this. So statisticians have pre-computed very accurate tabular listings of probabilities between 2 points, a and b, or maybe less than 1 point a. But the fact that the curve is symmetrical, I'll show how you use it to calculate other kinds of probabilities, right? You pretty much do everything here. But understand with a continuous variable, you're not interested in the value that x has a certain value. You're more interested that x is between a range or less than one value or more than a value, okay? So we talk about the standard normal variable now. The standard normal variable is given a symbol capital Z. The standard normal variable has a mean of 0 and a variance of 1. Okay. So if this is the distribution here, then we substitute 0 and 1 here. So this is 0, mean is 0, and the variance is 1. Okay. And the curve looks like this here. The probability that Z, which is the standard normal variable is Z, the probability that Z is less than or equal to some value A is given by the area under the curve from A go to the left, because any value less than A will be to the left of A. So this area going from A to the left of A, right? The entire area under the curve. Now the curve extends from positive infinity to minus infinity. Look at the range here. So you're integrating over an infinite length, but actually the area is less than 1. The total area under the curve is actually 1. So this area here from negative infinity to A is actually less than 1. It's point something, believe it or not, right? We refer to normal tables to find the cumulative probabilities, right? So normal tables give you cumulative probabilities of something happening, and that's what you really want. So we have this symbol phi, P-H-I, phi, capital phi. Capital phi of A is the probability that the standard normal variable is less than a value of A. And this is what we're going to be using here. This phi of A, this is what we're going to be using to find probabilities. It's a compact notation for the probability that the standard normal variable is less than some value A. And we will write all the other probabilities in terms of phi to make it easy to find. And we'll draw diagrams to make sure that we're doing the right thing. So this is the standard normal tables here. It looks complicated, right? You see to the top right corner, the curve phi of Z is a shaded area here, right? They're using common Z to mean a value on the x-axis, right? We're using alpha, so we wouldn't get confused between the value A and the capital Z, which is the variable itself. So sorry, not alpha A. We're using A to mean a particular value that Z can have, and capital Z is the actual variable itself. And we will use this table here to find, I'll show you how to read this table now to find probabilities, right? So this is an image. You could right click and save it to your computer. So you see here, use the standard normal table to find these probabilities here. All right, so how you would do that? How you find phi of 0.16, sorry. That's the probability of the standard normal variable is less than 0.16. Okay, that's what this means, phi of 0.16. Now, 0.16, if you look at the diagram above, this tells you what the probability is, the area given a value of Z. So look Z here. Z is on the left here, and you read the values. The vertical column, the leftmost vertical column, is the first decimal place, as well as the whole number part. So 2.5, this is 2.5, right? The horizontal columns here is the second decimal place. 0 to 9 is the second decimal place. And the third decimal place, you have to add these columns here based on the number that it have. So let me look at this. Let me look at Z is less than 0.16, right? So we're looking for 0.16 as the value of Z. So we go 0.1, that's the second row here, right? And you go across, The second decimal place is 6. So you see here 5, 6, 36. That's what this is here from the table. So this is equal to 0.5636. Right? How did I get that? The first decimal place is 0.1. Second decimal place is 6. So where the 0.1 row intersect with the 6 column, we get 5636. This one probably cheated a couple of people. Some people probably get the wrong answer. 0.345, how we get this? So 0.34, so that's the fourth row, and this column here, the 4 column. So 0.34, that is 6331. And then in the same row, you go to the 5th column, any third decimal place. So that's 19. You see 5 being the third decimal place. It's still in the 0.3 row. It's still in the 0.3 row. It says 19. So we need to add 19 to 6331. So we come down here. You see I have 6331 and I add 19, I get 6350. So that's our probability, 6350, and the point is in front of the 6. Right? So knowing that that is how I had to do it, try finding these two probabilities here, right? It's always good to write it in this form, right? So let me see if I could do that. Oops. So this is 345. That's what phi of 0.345, that's what it means. The probability that the standard variable is less than 0.345. So do these two here. What is this? This is equal to, oops, 429. So 429. Duplicate this here. Put this 3.15. So copy that here. Right. So it have 3 decimal places. So anytime you see the value, the Z value, Z is a variable. This probability here, what the probability that Z is less than this value. When this Z value has a 3rd decimal place in it, you have to go to this rightmost column here, and you have to add whatever 2-digit or 1-digit value this is to the original probability here by adding it from the right-hand side. Okay. So try these two. Tell me answers again, and we practice some more. 429. How do you get 429? Right. So row 0.4, column 2. 0.4 row, column 2. That's 6628. Right. And then we look to the 9th column and the 3rd decimal place. So that's 32. So 6628 plus 32. That's what I have here. 6628 plus 32, I get 666. So the probability is 0.666. What about 3.159? So we have to go row 3.1. 5th column and the 9th or the 3rd decimal place column. So 3.15 is 3.15 is here. 3 9s on 184, and then we go to the 9th column here, which is 25, right? Because the 3.1, these three here, we add these columns to it, these values to rightmost it. But as soon as you drop down here and you get 39184, we have to use this row here, and the 9th column is 25. So we add in 25 to 999,184. So 999,184, we add 25, we get 999,209. That's the probability for that happening. Hope you all understand that. Okay, so use the standard normal table. What's the probability that Z, which is the standard normal variable, is less than 0.85? And then look at this probability here. What's the probability that Z is more than 0.85? What do you think about that? How you would find that probability? Remember, the table only gives the probability that Z is less than something. So to find Z is more than something, what would the shaded area look like? And then the total area under the curve is 1. So the area in one portion is equal to 1 minus the area in the next portion, right? So figure out how you would do this here. So what is the probability that Z is less than 0.85? So we go in to look at the 0.8 row, 5th column, right? But the 5 column. So 0.8, that's this row here. And the 5 column is 8023. So 0.8023. So you could actually read this off from the graph, from the table itself, right? So this is equal to 0.8023, right? You could read that off. That's because this is really phi, you could call it phi is the graph, right? So this is really phi of 0.85, because that's what the curve is. This curve up here is phi. You see a phi of Z, which is a cumulative probability that Z is less than this value here, whether it's positive or negative, it don't matter, right? But it's a less than probability. That's what phi is, right? But let's say a probability that Z is more than 0.85. You can't get that from this table. This table only gives less than a probabilities less than a certain value, not more than. But you use the properties of the curve, right? This is 1 minus the probability, 1 minus probability that is less than 0.5. Right? Which means there's 1 less than 1 minus phi of 0.85. This is 1 minus 8023. And that is, let me see, 19, 0.19. Look like 77. Oops. Oops. Right. Because, think of it as 8,023. 77 go take it to 8,100. Then a 900 will take it to 9,000. Then a 1,000 take it to 10,000, right? So that's how we had worked this out. So probability that Z is more than 0.85. If we look at the shaded diagram here, this is the white part of the area. That's the probability is more than the value. The curve phi of A is the cumulative probability that Z is less than A. That's a less than probability. That's an area to the left of the vertical line at A. We want the probability that is more than 0.85. So that's to the right. So just subtract it from 1. Okay. Now we have just showing you strategies here, right? If you notice, the table starts from A equals 0. Let's look at the table. Look, see it start from 0 up here. There are no negative values for Z. There are no negative values because we actually have to use the symmetry properties of the curve to find for that. So we could find for z less than a when a is positive, right? When a when a is less than or equal to, right? 0. That would work. But for negative values of a, yeah, we use the symmetrical properties of the curve. So let me look at this example here, right? So as the probability z is less than -1. So what is the mean of the standard normal variable? The mean is 0, right? The mean is 0. The x-axis, sorry, the y-axis passes through the point 0, right? So the mean is 0. Where's -1 relative to 0? It's on the left here. It's not on the right, it's the left. So this, if we draw a diagram for this here, let's see how this diagram would look. I remember I told you all you should probably draw diagrams, right? So look, this is the diagram here for probability z less than -1. -1 is to the left of 0. So that's a small probability. That's a probability less than 0.5. Remember, the total probability under the is the area under the curve, and the total area under the curve is 1, and the curve is symmetrical. So the area under the left side of the diagram is 0.5, and the area under the right side of the y-axis is 0.5. So that area there, that had to be less than 0.5 because it have this white area here on the left of the y-axis that is not covered. So how you'd find probability z less than -1. You can't read the table directly from that. But you could, the equivalent area is probably, let's look at, duplicate this. What's the probability that z is more than 1? What does that look like? Could you find that from the table? You should probably draw a sketch, right? So let's choose a sketch. This is probability that z is more than 1. Now, these two areas are the same because they're symmetrical. -1 is symmetrical with 1. This area here is equal to this area here. Both areas are equal. But what's the probability that z is more than 1? Again, you can't, none of these areas here you could find directly from the diagram, from the table. First of all, this one, we can't find probabilities for this because there's a negative value of a here, -1. The table starts from 0, it have no negative values on the left here, okay? And then we realize that this area is really this area here. But we can't use the table to find this either because this is the probability that z is more than something. The table gives the probability that z is less than something, right? There's an area to the left. But isn't probability that z is less than 1? Isn't this equal to 1 minus the probability that Z is less than 1, right? Because the total area under this curve here is 1. So this small area here is just 1 minus the big area, and the big area is probability that Z is less than 1. Okay? So this is 1 minus something. Was 1. Let's look for 1 in any table. That's really easy. Look 1.0. You say 1.00 is 8413.8413. 0.8413. So what is 1 minus 0.8413? So you get 0.87 and the 13. 87 and 13 is 100. I'll put it to 5 and you'll get a 1.5. Right, so 1587. Does the probability that Z is less than -1? So I could even write that here. This solution, we could duplicate it and we could write it. Probability that Z is less than -1. That's really what it is there. All right. So that's how you would find probability for a negative number, less than a negative number. We wanted to find this, but we use symmetry to show that is this. And then for this here, the second one, that's just 1 minus the bigger probability. That's the white area here, right? So try these. So try example 3. So these last two areas here were equal due to symmetry. So originally what I asked us, was it probability that Z is less than -1? That's this first area here. Well, this first area is equal to this area. And this area is 1 minus the white area, which is phi of 1, all right, which is 0.8413. So that's how we get this 0.1587. The next question asks us for, what is the probability that Z is more than -1? Again, you can't find that from the table because more than probabilities do exist in the table. The table is for less than probabilities for positive value. So you can't use the table to find less than probabilities for a negative value. And you can't use it to find more than probabilities, right? So what's the probability that z is more than -1? Now let's look at the diagram. -1 is less than the mean. The mean is 0, which is the center. So -1 is to the left. So this area here is more than 0.5. Because half the area under the curve is 0.5, and that area is a little more than half. But this area here by symmetry is equal to this area. Probability that z is less than 1. But this here you could find directly from the tables, right? Probability z less than 1 is equal to phi of 1. Okay, which directly from the tables is 8413. If you look 1.0, let's look at it here. 1.0 is here, 8413. Right? So I show you all how to deal with negative values, how to find the probability both less than and more than negative values and positive values. Okay. So to recap, try example 3. Okay. Always write your answer in terms of phi. Always say phi of something. All right. So I probably need to write that here. Let me see. This here. This is 1 minus 1 phi of 1. Right. Always write your answer in terms of phi. So I use phi there. Remember, what is phi? The probability that z is less than something. Right? We see we use it up here and here as well. Right? So always write your answer in terms of phi and the second to last stage. So change the probability to z less than some positive number, right? And that is what phi is. So you might have 1 minus that, or twice that minus 1, or 1 minus twice. So I have a lot of things, a lot of final answers you will get, but always write your final answer in terms of phi. So try example 3. So these are the solutions. It's helpful to draw some diagrams before using the tables, right? So probability that z is less than a positive value. That's where you could read off the table. But what's 1.3? Well, 0 is the mean, which is center, the origin. So 1.377 is to the right of it. So this is a probability bigger than 0.5. When you read it off the tables, you see it's 0.9158. This is directly phi of 1.377. How we find it? We do 1.37. 1.37, go up here. 1.3, as this row here. 7 is in 9147. And then 7 is the third decimal place. So you have the 11. So we add 11 to 9147. So 9147, 11, and 9150. That's why we get 0.9158. What's the probability that z is more than negative 1.370? Well, you just reflect the 1.3 in the y-axis and you'll get negative 1.377 here. Again, that probability is greater than, right? Z is greater than. So obviously this is the area to the right, which is greater than 0.5. By symmetry, z greater than negative 1.3 is the same as z less than positive 1.3, which is the area we had before. These two areas here that you're seeing here, they're the same by symmetry. So this is phi 1377, which is 9158. Look at this one here, probability that z is more than 1.377. There's a area to the right of a positive number. That's a small probability, it's less than 0.5. The whole area is 1, so this is 1 minus the white area. which is 1 minus phi of 1.377, which is 1 minus the value we got before, which is 0.0842. That answer kind of makes sense because there had to be a probability less than 0.5. And this area here, probability of Z is less than negative 1.377. That's an area to the left of a negative value. We cannot read that off the table. The tables only give positive values. So we say, well, okay, this area is the area before, which is Z is more than a positive number, which is 1 minus Z is less than a positive number, right? Which is the 1 minus the phi that we got before. So that's why I had to draw diagrams. They had to figure out where the value of A is. Do the shaded area. Is it a less than, which is area to the left, or is it more than, which is area to the right? That's how you all know how to switch it up. So answering these questions, once you have a diagram is nice, and the calculation, that's the complete solution. So I hope you all understand that. So we have 3 homework questions here for you to try. And I draw the diagram for the first one for you, right? So what's the probability that Z is between these two values? Z being the standard normal variable. So you should draw a diagram first and then work out how you're going to split up the areas to find that shaded area. So the first diagram, Z is between 2 positive values. So this area here is totally on the right-hand side of the y-axis. So this probability is less than 0.5. But how would you use the phi values, which is the values in the table, to find this probability here? Draw appropriate diagrams for the other 2 questions, and then use the table to figure out how you'll split up those areas into pieces, right? This is more along the lines of where you're going to be getting in your assignment. So have fun with this.